There's something coming toward us from the outer darkness. Not fast, not flashy, just inevitable. It's called Bernardinelli-Bernstein, a comet so massive it makes every interstellar visitor we've seen look like a pebble. 137 kilometres across, 10,000 times more massive than 3I Atlas, and it's been falling inward for millions of years. Scientists say it's a time capsule from the early solar system, a frozen relic carrying secrets from our cosmic birth. But others ask uncomfortable questions. Why is it coming now? What woke this giant after billions of years of sleep? And what if we're not ready for what it might reveal? Stay with me, because by the end you'll understand why this object changes everything. If you're as captivated by these cosmic enigmas as I am, go ahead and like and subscribe to stay in the loop as we track BB's journey toward the inner solar system. Leave a comment telling me where you're watching from, what hour it is in your corner of the world, and whether you think of this new comet. Part 1. Why this object isn't just big, it's wrong. Picture this. You're an astronomer. You've spent your career studying comets, small icy rocks that swing past the sun, light up for a few weeks, then vanish back into the void. You know their sizes, you know their behaviour, you've catalogued thousands of them, and then one day you find something that makes absolutely no sense whatsoever. In 2014, buried in archival images from the Dark Energy Survey, astronomers spotted an object. At first nobody paid much attention. Space is full of rocks. But as they tracked it, measured it, analysed it, something became clear. This wasn't just another comet. This was something fundamentally wrong. They called it C 2014 UN 271. Most people call it Bernardinelli-Bernstein, or just BB for short, and BB is enormous. When the Hubble Space Telescope finally got a good look at it, the measurements came back. The nucleus alone might be 85 miles across. That's roughly 137 kilometres of solid ancient ice and rock. To put that in perspective, most comets we know are just a few kilometres wide. BB is not a comet in the traditional sense. It's more like a dwarf planet that decided to pretend it was a comet. It's roughly 10,000 times more massive than typical objects we've seen passing through from interstellar space. Remember 3I Atlas? That tiny interstellar visitor that just zipped through our solar system? Atlas is small, fast, fragile. It came from another star system entirely, moving at breakneck speed. BB is the opposite. It's colossal, slow, stable. It's been part of our solar system for billions of years, lurking out in the Oortcloud, that vast spherical shell of icy debris that surrounds our sun at unimaginable distances, and now it's coming inward. Here's what makes BB truly bizarre. Comets aren't supposed to be this big. Our models of the early solar system suggest that most comets formed from small clumps of ice and dust. They're rubble piles, essentially, loose collections of material held together by weak gravity. But BB is different. Its size suggests it formed differently, perhaps as a protoplanet that never quite made it. It's not a rubble pile, it's solid, structured, and that raises uncomfortable questions. Why does something this massive exist in the Oortcloud? How did it get there? And why, after spending billions of years in frozen silence, is it suddenly active? Because here's the thing, BB started brightening years ago, way out beyond Neptune, where the sun's warmth is barely a whisper. Water ice can't sublimate at those distances. Water ice needs heat. But BB was glowing anyway. Something else was venting from its surface, something more volatile than water. In 2024, the Atacama Large Millimeter Array, ALMA, trained its radio eyes on BB. What they found was remarkable. Powerful jets of carbon monoxide, CO, erupting from specific regions on the comet's surface. This was happening at around 16.6 astronomical units from the Sun. For reference, Saturn orbits at roughly 9.5 AU. BB was way out there, and it was already active. Carbon monoxide sublimates at incredibly low temperatures, much lower than water. The fact that BB has enough CO to produce visible jets means it has massive internal reservoirs of this gas, preserved for billions of years. Most comets don't have that. Most comets are depleted of hypervolatiles like CO by the time we see them, but not BB. BB is a time capsule. Mainstream astronomers love this. They call it a pristine sample from the early solar system, a relic from the era when planets were still forming. Study BB, they say, and you're studying the raw materials that built worlds, and they're probably right. But there's another question lurking beneath the surface. A question that makes some scientists uncomfortable. Why now? If BB has been sitting in the Oort cloud for 4.5 billion years, undisturbed, why did it suddenly start falling inward? What changed? Was it purely random, just cosmic chance, or was there a trigger? Some theorists suggest galactic tides. Others propose a passing star. A few whisper about something else entirely, something unseen, something that nudged this giant awake and sent it tumbling toward the inner solar system. We'll explore those possibilities soon, but for now, sit with this. An object the size of a small moon, filled with ancient gases, moving on a trajectory that defies easy explanation, is heading toward the sun. And we have no idea what really set it in motion. That's not just interesting, that's terrifying. Because if we don't understand what woke BB up, how can we predict what else might be coming? How many more giants are out there in the Oort cloud waiting for the same mysterious push? And what happens if the next one isn't heading for a safe perihelion near Saturn? What if the next one is heading straight for us? Hold that thought, because the mystery of BB's awakening is about to get stranger, much stranger. Part 2, The Awakening in the Dark. Why now? Imagine a bowling ball sitting on the edge of an ice rink. It's been there for 1 million years, motionless, perfectly balanced, and then without warning it starts to roll. Slowly at first, almost imperceptibly, but it's moving. The question isn't whether it's moving. The question is, what pushed it? That's the puzzle of BB. For billions of years it sat in the Oort cloud, that vast halo of frozen debris surrounding our solar system. The Oort cloud extends from about 2,000 AU to as far as 100,000 AU or more. That's unimaginably distant. At those distances, the sun is just a bright star among many. Gravitational forces are weak. Objects drift. They orbit the sun on timescales of millions of years, and they're supposed to stay out there unless something disturbs them. So what disturbed BB? One hypothesis involves galactic tides. Our solar system doesn't exist in isolation. We're part of the Milky Way galaxy, orbiting the galactic centre. As we move through the galaxy, we encounter gravitational influences. The combined pull of countless stars, gas clouds, and dark matter creates tidal forces. These tides aren't constant. They oscillate. They pulse. And some dynamicists believe these pulses can perturb Oort cloud objects, nudging them inward. There's a specific model that's been circulating, a 14,400-year tide pulse scenario. The idea is that every 14,400 years or so, a particularly strong galactic tide sweeps through the outer Oort cloud. Objects at the very edge, like BB, feel that tidal pull. Over time, their orbits change, slowly, gradually, until one day they're no longer stable. They start falling inward. This model is speculative. It's not confirmed, but it fits some of the data. Then there's the passing star hypothesis. Our sun isn't alone in space. Stars move. They pass near each other. Millions of years ago, another star might have drifted through the outer reaches of the Oort cloud. The European Space Agency's Gaia mission has been mapping stellar motions across the galaxy. Some researchers have analysed Gaia data and suggested that a star did pass near our solar system in the distant past, close enough to gravitationally perturb distant comets. A passing star doesn't need to get very close. Even at a distance of several thousand AU, its gravity can tug on Oort cloud objects. These tugs are small, incremental, but over millennia they add up. An object's orbit shifts, its eccentricity changes, and eventually it begins its long fall toward the inner solar system. If this is what happened to BB, then its awakening wasn't random. It was inevitable, a delayed consequence of an ancient encounter. But here's where it gets uncomfortable. If either of these scenarios is true, if galactic tides or passing stars are responsible, then we should expect more objects like BB. Lots more. The Oort cloud contains trillions of icy bodies. If tidal forces or stellar flybys can shake them loose, then BB is just the beginning. And that raises a question nobody wants to ask out loud. How many more are coming? Not all astronomers accept these models. Some argue that random diffusion is enough. Objects in the Oort cloud naturally evolve over time. Their orbits slowly decay. No external trigger needed, just patience. Billions of years of patience. And eventually some fall inward. It's cosmic roulette. BB's number came up. That's all. But there's a problem with that explanation. It feels too convenient, too clean. Because BB isn't just any comet. It's massive, it's unusually structured, and its timing, arriving in our observational era, in the age of advanced telescopes, feels almost orchestrated. Almost like something wanted us to see it. That's where the whispers start. The quiet speculation, the uncomfortable theories. If not galactic tides, if not a passing star, then what? Could there be something else out there? A hidden planet? A dark matter clump? Something we haven't detected yet? Something that's been quietly perturbing oortcloud objects for eons? There's a story. A researcher, someone respected in the field, once told colleagues over drinks, "I don't believe in hidden planets. I really don't." But something huge must have disturbed that object. The math doesn't work otherwise. The odds are too low. And when the math doesn't work, either your assumptions are wrong, or there's something you're not seeing. So which is it? Are our assumptions wrong? Or is there something out there we're not seeing? And if there is, why can't we find it? Why does it remain hidden? Is it simply too faint, too far, too small to detect? Or is it something stranger, something our instruments aren't designed to recognize? We'll explore those possibilities soon. But first, we need to understand BB's orbit, because its trajectory holds clues, big, unsettling clues. And those clues suggest that whatever woke BB up, it didn't just give it a gentle nudge, it fundamentally altered the geometry of its path through space. And that geometry is deeply, profoundly weird. Part 3. The perpendicular orbit nobody expected, and why it matters. Orbits tell stories. If you know how to read them, they reveal where an object came from, what forces shaped it, and where it's going. Most objects in our solar system orbit in roughly the same plane. The planets, asteroids, most comets, they all circle the Sun in a relatively flat disk called the ecliptic. This makes sense. The solar system formed from a rotating disk of gas and dust. Everything inherited that rotation. Everything orbits in the same general direction at similar angles, except BB. BB's orbit is tilted at about 95.5 degrees relative to the ecliptic. That's nearly perpendicular. Imagine the planets orbiting the Sun like runners on a track. BB isn't on the track. It's coming in from above, cutting straight down through the plane. That's bizarre. That's not how comets are supposed to behave. Why does this matter? Because inclination tells you about an object's dynamical history. Low inclination orbits suggest an object formed in the protoplanetary disk and stayed there. High inclination orbits suggest something violent happened. A gravitational interaction, a close encounter, something that kicked the object out of the plane. And near perpendicular orbits, those suggest chaos, deep, ancient chaos. One explanation is the deep Oort chaos model. The Oort cloud isn't uniform, it's not a calm, orderly shell of ice. It's dynamically hot. Objects out there move in all directions, at all inclinations. They've been jostled by passing stars, galactic tides, planetary perturbations over billions of years. By now, the Oort cloud is a chaotic mess. Objects orbit every which way. So maybe BB's perpendicular orbit isn't unusual. Maybe it's just a product of that chaos. But there's another idea, a more controversial one. What if BB isn't originally from our solar system at all? What if it's a captured interstellar object? Billions of years ago, during the early days of the solar system, stars were closer together. Planetary systems were still forming. Objects drifted between stars. Some got captured, trapped in another star's gravity well, stuck in the Oort cloud, waiting. If BB is a captured interstellar object, that would explain its weird orbit. It came from somewhere else. Its inclination reflects its origin, not ours, and now, after billions of years in exile, it's finally falling inward. This theory is speculative. There's no direct evidence, but it fits. Compare BB to 3I Atlas. Atlas came through on a hyperbolic trajectory. It entered the solar system, swung past the Sun, and left. Never to return. It was clearly interstellar. But BB is bound to the Sun. It's on an elliptical orbit. It'll swing inward, reach perihelion, then head back out. It's not leaving. It belongs here. Or at least, it's been here long enough to belong. Orbital mechanics are unforgiving. BB's inclination affects everything. How it interacts with the giant planets. How solar radiation heats its surface. How outgassing jets behave. As it moves inward, it'll cross the orbital planes of Saturn, Jupiter, maybe even the inner planets. Each crossing is a potential gravitational encounter, a chance for its orbit to change. There's a concept in celestial mechanics called orbital resonance. When two objects have orbital periods that are simple ratios of each other, they can influence each other profoundly over time. Jupiter and Saturn are in near resonance. Their gravitational dance shapes the entire outer solar system. Could BB enter a resonance with one of the giant planets? Could that change its path? Make it more dangerous? More unpredictable? It's possible, unlikely, but possible. And that uncertainty bothers astronomers, because we like predictability. We like knowing where things are going. But BB's orbit, with its steep inclination and uncertain perturbations, introduces chaos. And chaos is hard to model, hard to predict, hard to prepare for. Some theorists find the inclination unsettling for another reason. They argue it feels engineered, not naturally evolved. As if something deliberately placed BB on this trajectory. That's fringe thinking. Most scientists dismiss it. But the feeling persists. The orbit is just too specific, too unusual, too unlikely. Could a phantom planet have pumped BB into this orbit? Could an unseen massive body, lurking beyond Neptune, have gravitationally sculpted BB's path over millions of years? We'll explore that idea soon. But for now, consider this. An object's orbit is its fingerprint. It tells you its history. And BB's orbit tells a strange, uncomfortable story, a story of forces we don't fully understand, a story of something, somewhere, exerting influence we can't quite see. And if we can't understand BB's orbit, how can we understand what's inside it? How can we predict what it'll do as it gets closer to the sun? Because what's happening on the surface, those jets of carbon monoxide, those bursts of light, they're just symptoms. The real mystery is inside that massive nucleus, inside the structure of the object itself. And recent observations are giving us our first tantalizing glimpses of what BB really is. And it's not what we expected. Part 4. Internal structure. The monster made of layers. Comets don't like to give up their secrets. You can watch them from Earth. You can send spacecraft to fly past them. But understanding their internal structure? That's hard. Really hard. Because you can't crack one open. You can't drill into it. You have to infer. You have to deduce from limited data. And in the case of BB, that data is both fascinating and deeply puzzling. The Hubble Space Telescope has been watching BB for years now. Hubble is good at imaging. Really good. And what Hubble saw surprised everyone. BB's nucleus isn't jagged. It's not an irregular rubble pile like most comets. It's nearly spherical, smooth, uniform. That suggests something important. It suggests internal forces shaped this object. Gravity, perhaps, or thermal processes. Something that moulded it into a sphere over billions of years. Spherical objects in space usually fall into two categories. Planets and moons, held together by strong gravity. Or differentiated bodies, where heavier materials sink to the centre and lighter materials rise to the surface. BB is too small to be a planet, but it might be differentiated. It might have layers, an outer crust, a mantle of different ices, maybe even a core of the rock and metal. That would make it more like a miniature planet than a comet. ALMA, the radio telescope array in Chile, added another piece to the puzzle. In 2024, ALMA mapped carbon monoxide jets erupting from BB's surface. These weren't random bursts. They were organised, emerging from specific regions, persistent over time. That tells us something crucial. The interior isn't uniform. There are pockets of volatiles, reservoirs of CO trapped beneath the surface, and as BB moves closer to the sun, those reservoirs heat up. The pressure builds, and eventually the gas escapes. Carbon monoxide is a hypervolatile. It sublimates at incredibly low temperatures, much lower than water. The fact that BB has enough CO to produce visible jets at 16 AU means its interior is loaded with this stuff. Most comets lose their CO quickly. It vents away early in their lives, but not BB. BB has been cold enough, for long enough, to preserve massive amounts of CO deep inside. That's extraordinary. Here's where it gets speculative. Some researchers propose a stratified chemistry model. Imagine BB like an onion, layers upon layers. The outermost layer is a crust of silicates and refractory materials. Beneath that, a layer of water ice mixed with organics. Deeper still, carbon dioxide ice. And at the core, perhaps, pockets of pure CO. Each layer formed at different temperatures during the solar system's early days. Each layer preserved by the freezing cold of the Oort As BB approaches the Sun, these layers heat up sequentially. First, the outermost crust warms, then water ice starts to sublimate, then CO2, then CO. Each phase produces different outgassing behaviour, different jets, different brightness. And what we're seeing now at 16 AU is just the beginning. The CO layer is starting to vent, but the deeper layers are still frozen, still waiting. There's another idea floating around, phase-trapped hypervolatiles. This is the notion that certain volatile compounds can exist in unusual crystalline structures at very low temperatures, structures that trap gases inside, and those structures only break down when warmed to specific temperatures. So maybe BB has been sitting out there with CO locked inside weird ice crystals. And now, as it warms, those crystals are breaking. The CO is escaping, and that's driving the activity we see. This has mechanical implications. Internal pressure from trapped gases can fracture the crust, create cracks, fissures, and those fissures become vents, jets. Over time, as more gas escapes, the structure weakens, fragments break off, the comet changes shape. Some comets fragment dramatically when they get close to the Sun. Will BB? Nobody knows. But the possibility is there. What we do know is that BB isn't behaving like a typical small comet. Small comets have erratic jets, random bursts of activity. But BB's jets are organised, powerful, persistent. That suggests an internal engine, a system of vents and reservoirs working in concert. And that's not typical. That's weird. That's the kind of behaviour you'd expect from a cryovolcanic world. A small icy moon with internal heat, not a comet. So what is BB really? Is it a comet? Is it a dwarf planet? Is it something in between? And does it matter? Well, yes, it matters a lot. Because how we classify BB determines how we study it, what questions we ask, what missions we propose, and what dangers we prepare for. Because if BB is more planet-like than comet-like, then its behaviour near perihelion could be radically different. More violent, more unpredictable, more spectacular, but we're getting ahead of ourselves. Because before we can plan how to study BB up close, we need to understand its timeline. How long do we have? When will it get close? And what does that mean for our observation window? Because here's the uncomfortable truth. BB is moving slowly, majestically, like a skyscraper drifting through space. But that slowness is deceptive, because time is running out. The window to study this object, to really understand it before it changes forever, is narrower than you think. Part 5, a slow-motion approach, but a fast-moving mystery. Imagine a skyscraper made of dirty ice. Not a metaphor. Literally a building-sized structure, frozen solid, coated in ancient organics, drifting through the void. That's BB, and it's coming, slowly, inexorably, heading inward toward the Sun. But here's the paradox. Even though it's moving slowly, there's urgency, because every year that passes, BB changes, and once it changes too much, we lose our chance to study what it really was. BB was first spotted in archival images from the Dark Energy Survey in 2014, but it wasn't identified as unusual until later. By the time astronomers realised what they were looking at, BB had already been moving inward for years, maybe decades, maybe centuries. Its orbit suggests it started falling from the Oortcloud long before humans invented telescopes. We just happen to notice it now. Right now, BB is still far from the Sun, beyond Neptune, moving slowly through the outer solar system. Its current distance fluctuates as it orbits, but during recent observations it was around 16 to 18 astronomical units out. For context, Neptune orbits at about 30 AU, Saturn at 9.5, Jupiter at 5, BB is still in the outer neighbourhood, but it's heading inward, and we know where it's going. Astronomers have calculated BB's trajectory with high precision. It will reach perihelion, its closest approach to the Sun, in January 2031, and perihelion will be at about 10.9 AU, just beyond Saturn's orbit. Not close by any means. BB won't threaten Earth, it won't come anywhere near the inner planets, but 10.9 AU is close enough for solar heating to change everything. Here's the window. Between now and 2028, maybe 2029, BB will undergo its most dramatic transformation. Right now, it's venting CO, subtle jets, gentle outgassing. But as it gets closer, water ice will start to sublimate. The coma, that fuzzy cloud of gas and dust around the nucleus, will thicken. Jets will intensify. The comet will brighten. And all of that activity will make it harder to study the nucleus itself. Harder to see what's really happening beneath the surface. So the most valuable observations need to happen now, in the next few years. Before BB gets too active, before the coma obscures everything, scientists are scrambling, Hubble is watching, ALMA is listening, ground-based telescopes are tracking, large optical surveys are capturing data. Every observation adds a piece to the puzzle. Every spectrum reveals a new molecule. Every image shows subtle changes. But there's never enough time, never enough data, never enough certainty. There's another risk: fragmentation. Some comets don't survive their close approach to the Sun. They break apart, disintegrate under thermal stress and rotational forces. If BB fragments, that's both a disaster and an opportunity. A disaster because we lose the intact object, we lose the pristine interior, but an opportunity because fragmentation exposes fresh material. Interior ices that have never seen sunlight. And that material could tell us everything. Will BB fragment? Nobody knows. Its size suggests stability. Large objects are held together by stronger gravity. They're less likely to break apart, but internal pressure from outgassing could weaken the structure, create faults, and if BB has a layered interior like we suspect, those layers might separate under stress. Imagine peeling an onion, layer by layer, each fragment revealing a different epoch of solar system history. Even if BB doesn't fragment, its appearance will change dramatically. Right now, it's a faint smudge, visible only to large telescopes. But by 2030, 2031, it could be bright enough to see with amateur equipment. Not naked eye, but a decent telescope could spot it. Imagine that. A comet the size of a small moon, glowing in the outer solar system, visible to anyone with the patience to look. That's rare, that's special, but it's also temporary. After perihelion, BB will swing back outward. It'll fade, cool down, retreat into the darkness. Its orbital period is millions of years. Once it leaves, it won't be back. Not in our lifetimes. Not in our civilization's lifetime. This is a once-in-species opportunity, a chance to study an object that has existed, unchanged since the solar system was young, and we're living through it, right now. So the urgency is real. Scientists are pushing for more telescope time, more observations, more data. Some are even proposing missions. Crazy, ambitious missions to send a probe to BB, to fly past it, to study it up close. Most of those proposals are pipe dreams. The engineering is too hard, the funding isn't there, but the desire is real. Because we know what's at stake. We know what we'll lose if we don't act. And here's the haunting part. We're not just watching a comet. We're watching something ancient and vast awaken. Something that has slept in the cold dark for billions of years. And now, for reasons we don't fully understand, it's waking up, moving, changing, heading toward the sun. And we may never fully understand why. We may never know what set it in motion, what forces, what events, what invisible hands guided this giant out of the shadows and into our view. But it's here now, and it's watching us as much as we're watching it. And that thought, that uncomfortable existential thought, should keep us all awake at night. Part 6. What if it's not alone? The clustering problem. Patterns matter. In science, in nature, in the cosmos, patterns tell you something is happening. Something real. Something that demands explanation. And right now, there's a pattern emerging in our solar system that's making astronomers very uncomfortable. Because over the last decade, we've detected a cluster of unusual objects entering or passing through our neighbourhood. And the odds of that being random, they're disturbingly low. Let's rewind. October 2017, astronomers spot 1I/Oumuamua, the first confirmed interstellar object ever detected passing through our solar system. It's small, elongated, tumbling. It doesn't behave like a comet. No visible coma, no jets. But its trajectory bends slightly as it passes the sun, suggesting some kind of outgassing. Scientists argue for months about what it is. Asteroid? Comet? Something else? To this day, nobody knows for sure. But one thing is certain. It came from another star. It passed through, and it left. August 2019, 2I/Borisov arrives. Another interstellar object, but this one is clearly a comet. Visible coma, gas jets. Spectroscopy reveals familiar molecules, carbon monoxide, water, cyanogen. Borisov behaves like comets from our own solar system. That's reassuring. It suggests comet chemistry is universal. But it also raises a question. If interstellar comets are common, why did we only start seeing them in 2017? 2025? 3I Atlas shows up, small, fast, interstellar, barely studied before it leaves. And now we have BB. Not interstellar, but massive, ancient, anomalous. 4 unusual objects in less than a decade. Is that normal, or is something happening? The observational bias argument says yes, it's normal. Our telescopes are better now. Surveys are more comprehensive. We're scanning more sky, more often, with better sensitivity. Of course we're finding more objects. We're looking harder, that's all. Nothing mysterious about it. Just better technology revealing what was always there. But some dynamicists aren't convinced. They've run the numbers. They've calculated the expected rate of interstellar object encounters based on stellar densities, velocity distributions, and gravitational cross-sections, and the numbers don't quite add up. We're seeing more than we should, not by a huge margin, but enough to notice, enough to wonder. If the cluster is real, if it's not just observational bias, then something is happening. And the most likely explanation involves the Oort-cloud, because the Oort-cloud is vast, enormous. It contains trillions of icy bodies, and it's not static, it's dynamic. Objects move, drift, get perturbed, and if something's perturbing them more than usual, if some external force is shaking the Oort-cloud, then we'd expect more objects to fall inward. More comets, more anomalies, more surprises. This leads to the trans-Oort perturber hypothesis, the idea that something massive, something we haven't detected yet, exists beyond the Oort-cloud and is gravitationally stirring things up. Not Planet 9, not necessarily, but something. Maybe a substellar object, a brown dwarf that passed through the outer solar system millions of years ago, or maybe a dense clump of dark matter, or maybe something we haven't even conceived of yet. The hypothesis is speculative. There's no direct evidence, but it's tantalizing, because it explains the cluster. It explains why BB and other objects are arriving now. It suggests an external trigger, an event in the recent past, astronomically speaking, that disturbed the Oort-cloud and set multiple objects on inward trajectories. And if that's true, then BB isn't alone. There are others, already on their way. Objects we haven't detected yet. Giants lurking in the dark, slowly falling toward the inner solar system. Critics caution restraint. Selection effects are powerful. Telescopes are biased toward finding unusual objects because unusual objects are interesting. Funding goes to surveys that discover weird things. Careers are built on anomalies. So maybe we're overinterpreting. Maybe the cluster is an artifact of human curiosity, not cosmic reality. Maybe there's nothing unusual happening at all. But there's a story. A researcher who ran simulations, thousands of them, modelling Oort-cloud dynamics under various conditions, and the code kept failing to produce the observed cluster. Not unless they added something else. An external perturber, a hidden mass, something that wasn't supposed to be there. And when they added it, the simulations matched reality. The cluster appeared. The objects fell inward. The timing worked, and the researcher quietly, reluctantly told colleagues, "I don't know what it is, but something's out there." So what is it? What could perturb the Oort-cloud on this scale? A rogue planet? A dark matter structure? Something even stranger? And if it exists, why haven't we found it? Why does it remain hidden? Because if there's one thing scientists hate, it's invisible forces. Invisible forces feel like magic. And science isn't supposed to need magic. Science is supposed to explain things. But right now, we don't have an explanation. We have a cluster, a pattern, and a growing suspicion that the outer solar system is hiding something big. And speaking of hidden things, there's one candidate that keeps coming up in conversations. One ghost that refuses to die. One hypothesis that explains so much, yet remains frustratingly elusive. It's called Planet 9, and it might be the key to understanding everything. Part 7, the Planet 9. Ghost? A threat? A myth? Or a convenient placeholder? Ghost stories are compelling because they're unfalsifiable. You can't prove a ghost doesn't exist. You can only fail to find it. And Planet 9 is the ultimate ghost story of modern astronomy. A massive planet, 5 to 10 Earth masses, lurking in the outer solar system, far beyond Neptune, too faint to see, too distant to detect, but maybe, just maybe, real. The hypothesis emerged in 2016. Astronomers noticed that several trans-Neptunian objects, TNOs, had unusually aligned orbits, their perihelia, the points, where they come closest to the Sun, clustered in the same region of space. That's weird. Random orbits shouldn't align like that, unless something is shepherding them. Something massive. Something with enough gravity to corral distant objects into similar paths. So they proposed Planet 9, a super-Earth ejected from the inner solar system during the early chaotic period when planets were still forming. It got kicked outward by Jupiter or Saturn, settled into a distant eccentric orbit, and it's been out there ever since, invisible, silent, but gravitationally active, slowly sculpting the orbits of TNOs over millions of years. The hypothesis is elegant. It explains the orbital clustering. It explains some of the weird inclinations. It even predicts where Planet 9 should be. Roughly, sort of. The problem is, nobody can find it. Surveys scan the predicted region. Nothing. Deep imaging campaigns? Nothing. Infrared searches? Nothing. If Planet 9 exists, it's either fainter than expected, or in a different location, or both. And that's where things get murky. Because in 2024 and 2025, new papers started circulating. Some supported Planet 9, others proposed alternatives, and a few suggested that the whole thing might be a statistical fluke. One alternative is the self-gravitating disk instability model. Instead of a single planet, imagine the outer solar system contains a disk of small bodies, thousands of them, and this disk has enough total mass to gravitationally interact with itself. Clumps form. Those clumps perturb other objects, and over time, you get orbital clustering without needing a single massive perturber. It's collective gravity, emergent structure, no Planet 9 required. Another alternative is the phantom perturber, not a physical object at all, just a gravitational signature. Maybe it's dark matter. Maybe it's a transient structure that passed through the outer solar system millions of years ago and is now gone. Maybe it's an artifact of how we model gravity at extreme distances. The math works, the observations fit. But there's nothing actually there. Here's why this matters for BB. If Planet 9 exists, or if some massive perturber exists, it could have nudged BB inward. It could have destabilized BB's orbit millions of years ago, setting it on a collision course with the inner solar system. And if that's true, then BB isn't a random comet. It's a victim, an object pushed by unseen forces, and those same forces could be pushing others. But what if Planet 9 doesn't exist? What if the orbital clustering is just noise? What if we're seeing patterns where none exist? Then BB's journey is random, chance, cosmic roulette. And that's almost scarier, because randomness means unpredictability. It means we can't forecast what's coming. We can't prepare. We can only watch and hope. Some researchers argue the Planet 9 signal could be a statistical fluke. Surveys are biased. They focus on certain regions of the sky. Bright objects get noticed. Faint objects don't. And when you correct for those biases, the orbital clustering might disappear. The whole hypothesis collapses. Planet 9 becomes a mathematical ghost, a convenient placeholder for our ignorance. But then there are the true believers, the astronomers who've spent years searching, who've refined their models, who've mapped every possible hiding spot, and they're not giving up. Because even if Planet 9 isn't where they expected, even if it's fainter or smaller or on a different orbit, the gravitational effects are real. Something is out there. Something has to be. And then there's the truly speculative stuff. The ideas that make mainstream astronomers uncomfortable. What if Planet 9 isn't a planet at all? What if it's a primordial black hole? A tiny one formed in the first fraction of a second after the Big Bang. Mass equivalent to 5 Earths, but compressed into an object the size of a grapefruit. It would have the right gravitational signature. It would explain why we can't see it. And it would be utterly bizarre. Or maybe it's a dense knot of dark matter. Dark matter clumps on large scales. We know that. But could it clump on small scales too? Could there be a dark matter concentration in the outer solar system, massive enough to perturb orbits but invisible to every telescope we have? Some physicists say yes, others say no. Nobody knows for sure. There's a story about an astronomer who once joked, "If I find Planet 9, I'll name it after my dog, but I might never find it." Because the outer solar system is vast. Really vast. And searching for a faint object in that much space is like searching for a needle in a haystack the size of a continent. You could search for decades and miss it by a few degrees, or it could be right there, hiding in plain sight, and you'd never know. But here's the existential question. Does it matter? Does it matter if Planet 9 is a planet, a black hole, a dark matter clump, or nothing at all? Because regardless of what's out there, the effects are real. Objects are being perturbed, BB is falling inward, the clustering is happening, and something, somewhere, is pulling strings. And that something could tell us profound things about how the solar system works, about what forces shape planetary systems, about what's possible in the universe. And maybe, just maybe, BB isn't even a comet. Maybe it's something else entirely. Something that challenges our definitions. Something that sits on the boundary between comet and planet. Between natural and unnatural. Between expected and impossible. Because the more we learn about BB, the more it feels wrong. Not just unusual. Wrong. Like it doesn't quite belong in the categories we've built. And that raises the most uncomfortable question of all. What exactly is BB? Part 8. When a comet is too big. The dwarf planet hypothesis. Definitions matter in astronomy. They're not just semantic, they shape how we think about objects, how we study them, how we classify them. And right now, BB is breaking the definitions. Because by every traditional measure, BB is a comet. It has a coma, it has jets, it's venting gas. But by size, by structure, by composition, it's something else. It might be a dwarf planet, and if that's true, then everything changes. Let's start with the evidence. Size. BB's nucleus is roughly 85 miles, 137 kilometres across. That's enormous for a comet. Typical comets are a few kilometres, maybe 10 at most, but 85, that's in dwarf planet territory. Pluto's moon, Charon, is around 1,200 kilometres. Ceres, the largest object in the asteroid belt, is about 950 kilometres. BB is smaller, yes, but it's in the same ballpark. It's not a tiny ice ball, it's a world. Then there's shape. Hubble images show BB is nearly spherical. That's important. Small objects, held together by weak gravity, are irregular, lumpy, but large objects, with stronger gravity, pull themselves into spheres. It's called hydrostatic equilibrium, and it's one of the criteria for being a planet or dwarf planet. BB has it. That suggests significant self-gravity. That suggests internal pressure. That suggests it's more than just a rubble pile. Now consider composition. ALMA detected carbon monoxide jets. Powerful ones, persistent ones. That means BB has massive internal reservoirs of CO. Most comets lose their CO early. It vents away because it's so volatile. But BB? BB has held onto it for billions of years. That requires a specific structure. Layering. Maybe even differentiation. Heavier materials sinking to the centre. Lighter materials rising to the surface. Just like a planet. Some scientists are proposing a cryovolcanic preconditioning model. The idea is that BB, over billions of years, experienced internal heating. Not from the sun, from radioactive decay. Elements like aluminum-26, potassium-40, uranium. These decay, they release heat, and in a large enough object that heat can build up. Warm the interior, create liquid pockets, cracks, pathways for gas to escape. Imagine it like this. BB formed in the early solar system. It was a protoplanet, a building block for something larger, but it got ejected before it could finish growing, kicked out to the Oortcloud, frozen solid. But inside, radioactive decay continued, slowly, over billions of years, warming the core, fracturing the crust, building pressure. And now, as BB moves inward and solar heating adds to that internal warmth, the pressure is releasing, the gas is venting. The jets we see aren't just sublimation, they're cryovolcanic eruptions, mini-volcanoes of frozen gas. If this is true, if BB is a proto-dwarf planet with internal heat, then studying it becomes incredibly valuable. Because we've never seen an object like this up close. We've studied comets, We've studied dwarf planets, but we've never studied something in between, something that's transitioning, something that's waking up after billions of years of dormancy. What would that look like near perihelion? Cryovolcanic eruptions, dramatic jets, massive outgassing, maybe even surface changes, fractures opening, chunks breaking off, temporary atmospheres forming and dissipating. It would be spectacular, a once-in-a-lifetime event, and we'd have front-row seats. But here's the problem. If BB is more planet-like than comet-like, then missions to study it become even more important and even more difficult. Because dwarf planets are complex, they have geology, internal structure, active processes. You can't understand them from a distance. You need to get close, land on them, drill into them, and that's nearly impossible with current technology. Not everyone accepts the dwarf planet hypothesis. Critics point out that BB's activity is consistent with normal comet behaviour, just scaled up. Bigger object, bigger jets, nothing exotic required, no internal heat, no cryovolcanism, just a lot of CO sublimating as it approaches the sun. Occam's razor. The simplest explanation is usually right, but there's a middle ground. The hybrid object concept. Maybe BB is transitional. Not fully comet, not fully dwarf planet. Something in between. An evolutionary link. A snapshot of how small icy worlds grow and change. And studying it could tell us how Pluto formed, how Eris formed, how all the dwarf planets in the outer solar system came to be. There's a story. A planetary scientist, after reviewing Hubble data and ALMA observations, remarked to a colleague, "If this thing is a dwarf planet, then we just discovered a missing link in the family tree of the solar system, and we didn't even know we were looking for it." That's the beauty and frustration of astronomy. Sometimes you find things you weren't searching for, and those things change everything. So what is BB? Comet, dwarf planet, hybrid? Does it matter? Yes. Because classification determines study. It determines funding. It determines missions. And it determines how we think about the outer solar system. If BB is unique, then it's a curiosity. Interesting, but isolated. But if BB represents a class of objects, if there are more proto-dwarf planets lurking in the oortcloud, then the outer solar system is far more complex than we thought, far more active, far more dangerous. And that brings us to the whispers, the speculation, the uncomfortable theories that float around in private conversations, because some people, not many, but some, are asking a bolder question. What if BB isn't natural at all? What if it's something else, something artificial? And before you dismiss that as absurd, let's examine why people are even asking. Part 9. The Artificial Body. Whisper Network. Conspiracy theories start in the gaps, in the places where data is sparse and explanations are weak, and right now, BB has gaps, big ones. Its brightness is unusually stable, its jets emerge from the same regions persistently, its orbit is weirdly specific, and when scientists can't fully explain something, other people fill in the blanks, sometimes with wild speculation, sometimes with uncomfortable questions, and sometimes, rarely, with ideas that turn out to be right. Let's be clear. There is no evidence that BB is artificial. None. Zero. But there's a whisper network. Forums, blogs, think pieces. People pointing at anomalies and asking, what if? So let's address it. Not because it's likely, but because ignoring fringe theories doesn't make them go away. It makes them fester. So let's engage, rationally, and see what holds up. First claim. BB's light curve is unusually stable. Most comets fluctuate. They brighten and fade erratically as they rotate and vent gas. But BB's brightness changes are smooth, predictable, almost too regular. Some argue that suggests structural stability, like a rigid object, not a loose rubble pile. And if it's rigid, if it's engineered, maybe that explains the stability. Counterpoint. Large objects rotate more slowly. They have more inertia. Their light curves naturally smooth out. And BB is large. So stable brightness isn't suspicious, it's expected. No artificial structure needed. Second claim, the jets. ALMA mapped CO jets emerging from specific regions on BB's surface, and those regions seem to vent persistently, always the same spots. Some people argue that feels designed, like vents on a spacecraft, controlled, deliberate. Counterpoint. Cometary jets often emerge from specific regions called active areas. These are places where the surface is fractured or where subsurface ice is exposed. Once established, these vents can remain active for years. It's geology, not engineering. Natural processes create persistent features all the time. Third claim, the orbit, 95 degrees inclination, nearly perpendicular to the ecliptic. Some argue that feels placed, like something deliberately put on that trajectory. Why would a natural object have such a specific orbit? Counterpoint. High inclination orbits are common in the oortcloud. Dynamical interactions, galactic tides, passing stars, all these sculpt orbits over billions of years. Perpendicular inclinations aren't common, but they're not impossible. And one unusual orbit doesn't mean artificial origin. It means unusual history. So scientifically, the artificial hypothesis falls apart. But let's go further. Let's speculate. What if BB were artificial? What would that even mean? What could it be? A probe? Some suggest BB could be an alien probe, sent by an advanced civilization to study our solar system, disguised as a comet to avoid detection, moving slowly to gather data over long timescales. It's a romantic idea, but it raises questions. Why disguise it? Why not communicate? Why wait billions of years? And how would you even build something that large? A storage facility. Another idea, maybe BB is a data vault, a cosmic hard drive, built by a civilization that wanted to preserve information across deep time. They hollowed out a comet, filled it with data storage, and sent it drifting through space, waiting to be discovered, waiting to be decoded, a seed ship. Perhaps BB is a terraforming vessel, filled with microorganisms, genetic material, technology, sent to colonize new systems. It drifts, waits, and when it encounters a suitable star, it activates, releases its payload, begins the slow process of seeding life. These ideas are fun, imaginative, but they're not science, they're science fiction, and there's a reason. Because every one of these scenarios requires assumptions that aren't supported by data. BB's spectroscopy shows normal cometary molecules, CO, water, organics, no exotic compounds, no artificial emissions, no radio signals, nothing that screams engineered. Scientists test artificial hypotheses all the time. They model light curves, compare thermal emissions, analyze rotation rates, and every test comes back negative. BB behaves like a natural object. A weird natural object, yes, but natural. Yet the whispers persist, and there's a reason for that. Because humans are pattern-seeking creatures. We want meaning, we want agency, we want to believe we're not alone. And when we see something unusual, something that doesn't fit our models, part of us wonders, could this be it? Could this be the sign we've been waiting for? The answer, almost certainly, is no. But the question itself is valuable, because it forces us to think carefully about what we mean by natural, what we mean by artificial, and what we'd look for if we really wanted to find evidence of extraterrestrial engineering. And so far, BB doesn't fit the profile. But here's the uncomfortable truth. If an advanced civilization did want to send something through our solar system, disguising it as a comet would be brilliant. It would move slowly, naturally, unthreateningly. We'd assume it was ours. We'd study it. And by the time we realize what it was, it would be too late. Or too far. Or too strange to comprehend. That's the nightmare scenario. And it's almost certainly not happening. But almost is doing a lot of work in that sentence. Because we don't know. Not for sure. And we won't know until we get close. Until we send a probe. Until we see BB up close and confirm definitively that it's just a comet, just a natural object, just a relic from the early solar system. But sending a probe, that's the problem, because getting to BB is nearly impossible. Part 10. Mission impossible? Why touching BB is nearly off the table. Space missions are hard, really hard. Getting a spacecraft from Earth to another planet requires precise calculations, enormous energy, and years of planning. But getting to BB, that's on another level entirely, because BB isn't just distant, it's on a perpendicular orbit, and changing. A spacecraft's inclination by 95 degrees. That's one of the most expensive maneuvers in orbital mechanics. Let's talk delta V. That's the term for the change in velocity a spacecraft needs to accomplish a mission. More delta V means more fuel. More fuel means more mass. More mass means bigger rockets. And bigger rockets mean bigger budgets. For reference, getting to Mars requires about 6 kilometers per second of delta V. Getting to Jupiter, about 9, Getting to BB with its extreme inclination, easily 15 or more, maybe 20, that's in the realm of outer solar system missions like New Horizons, except harder. There's really only one plausible mission architecture, a Jupiter gravity assist. Launch a spacecraft toward Jupiter. Use Jupiter's massive gravity to bend the trajectory, change the inclination, redirect toward BB's orbital plane, and then cruise for years, decades maybe, until you intercept BB at some distant point in space. The launch window would be tight, probably somewhere between 2030 and 2034. After that, the geometry doesn't work. Jupiter won't be in the right position. BB will have moved. You'd have to wait for the next alignment, which could be decades away. So if we're going to do this, we need to decide soon. Like, really soon. But there are problems, big ones. First, power. At 11 AU, where BB will be near perihelion, solar panels are almost useless. You need nuclear power, a radioisotope thermoelectric generator, RTG. But RTGs are expensive, politically sensitive, limited in supply. NASA has a few, but they're allocated to flagship missions, not speculative comet flybys. Second, communication. At 11 AU, radio signals take over an hour to reach Earth. That's an hour each way, 2-hour round trip. You can't fly a spacecraft in real time at that distance. Everything has to be autonomous, pre-programmed, and if something goes wrong, you can't fix it. You just watch and hope. Third, navigation. BB is outgassing. That creates a coma, dust, gas, and all of that scatters light. Makes it hard to see the nucleus, hard to navigate precisely. A flyby mission needs to get within hundreds of kilometers to get good data. Miss by a few degrees, and you've wasted billions of dollars on fuzzy long-distance photos. Fourth, thermal control. BB is cold, really cold, and the spacecraft needs to survive that cold, while also dealing with occasional heating from its own electronics. Thermal management in deep space is tricky. Engineers have solutions, but they add mass, complexity, cost. Most mission planners look at these challenges and walk away. The risk is too high, the cost is too high, and the scientific return, while interesting, doesn't justify the investment. You could launch 3 Mars missions for the cost of 1 BB flyby, and Mars gives you more science per dollar. But there's a small group of mission designers who won't give up. They've been quietly drafting a concept, a lightweight, probe, minimal instruments, maybe just a camera and a spectrometer, launched as a ride share, piggybacking on another mission to reduce costs. It wouldn't orbit BB, it wouldn't land, just a fast flyby. Snap some pictures, grab some spectra, and send the data home. This ghost mission, as some call it, has never been officially proposed. It exists only in PowerPoint presentations and back-of-the-envelope calculations, but the idea is there, and if funding appeared, if political will aligned, it could happen. Barely. Just barely. There's also hope in future technology. Solar sails, nuclear electric propulsion, advanced ion drives. These technologies could change the equation, make high delta-V missions more feasible, more affordable, but they're not ready yet, not proven, not flight tested, and by the time they are, BB will be gone. So we're stuck. We have a unique, ancient object approaching, an object that could tell us how the solar system formed, how dwarf planets evolved, how the oortcloud works, and we might never touch it, never study it up close. We'll watch from a distance, take pictures, analyse spectra, and hope we're not missing something crucial. And that emotional tension, that frustration is real. Because science isn't just about knowledge, it's about curiosity, about pushing boundaries, about reaching out and touching the unknown. And when we can't, when the universe puts something just out of reach, it hurts. It reminds us how small we are, how limited, how trapped on this one pale blue dot. But here's the thing, even if we can't send a probe, we're still learning. Earth-based telescopes are incredibly powerful. Hubble, ALMA, the new James Webb Space Telescope. These instruments can see things we never thought possible. They can analyse atmospheres on distant planets, map molecular clouds in other galaxies, and they can study BB, watch it evolve, track its jets, measure its composition, and piece together its story. So maybe we don't need a mission. Maybe we already have what we need. Maybe the real breakthrough isn't touching BB, it's understanding it. From here, from home, using the tools we have. And maybe that's enough, or maybe it's not. Maybe there's something on BB's surface, something in its interior that we'll never see from Earth. Some crucial piece of the puzzle that requires hands-on study, and we'll never know because we didn't go. Because we chose safe, predictable missions over risky, ambitious ones. And future generations will look back and wonder, why didn't they try? That's the weight of this moment, the responsibility. Because BB is coming, and whether we study it up close or from afar, whether we understand it or not, it's going to change how we think about the outer solar system, how we think about comets, how we think about what's possible out there in the dark. And the real question isn't whether we can get there, it's whether we have the courage to try. Part 11. The 2025 Breakthrough in Dark Matter Mapping. The universe is mostly invisible. That's not poetry, that's physics. Roughly 85% of all matter in the universe is dark matter. We can't see it, can't touch it, can't detect it directly. We only know it exists because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters are too massive. Something invisible is pulling strings, and we call that something dark matter. For decades, we've assumed dark matter is smooth, a diffuse halo surrounding galaxies, gentle, uniform. But in 2025, that assumption started to crack. New gravitational lensing studies, combining data from multiple surveys, revealed something unexpected. Dark matter isn't smooth, it's granular, clumpy, lumpy, and those lumps might be smaller and denser than anyone predicted. Let me explain gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light. Einstein predicted this. We've confirmed it thousands of times, and by analysing how light bends, we can map the distribution of mass, including invisible mass, including dark matter. The 2025 breakthrough came from a team analysing data from the Euclid Space Telescope and ground-based surveys. They reconstructed the dark matter distribution in the local universe with unprecedented resolution. And what they found was shocking. Instead of a smooth halo, they saw structure, filaments, nodes, concentrations of dark matter far denser than expected on scales of just a few light years. Now here's where it gets interesting for BB, because the Oort sits at the edge of the solar system, roughly 1 light year out. And if dark matter clumps exist on light-year scales, they could pass through or near the Oort cloud, and when they do, they exert gravity. Weak gravity, yes, but over millions of years, weak gravity adds up. Could dark matter clumps be perturbing Oort cloud objects? Could they be the unseen forces nudging giants like BB inward? It's speculative, wildly speculative, but it's not impossible. Here's the problem: dark matter interacts only through gravity. It doesn't collide, doesn't scatter, just pulls. And individual dark matter particles have tiny mass. Even a clump of dark matter would have relatively weak gravitational influence compared to, say, a planet or a passing star. So could it really affect comet orbits? The math is tricky. Some cosmologists say yes. If dark matter clumps are dense enough, massive enough, and pass close enough, they could perturb distant objects. Others say no, the effects would be too small, too diffuse, lost in the noise of other gravitational influences. But there's a story. A cosmologist, after running simulations with the new granular dark matter models, told their team something unsettling. If I'm right, I just handed oortcloud theorists a wild card. Because if dark matter can clump this densely, we need to rethink everything we know about outer solar system dynamics, every perturbation calculation, every comet trajectory, everything. The implications are enormous. If dark matter shapes comet orbits, then predicting future inbound objects becomes vastly more complicated. Because dark matter is invisible, we can't track it, can't predict its movements. It's a random, unseen influence, like trying to predict billiard ball trajectories when invisible hands are randomly tapping the table. This ties back to BB, because BB's orbit, its timing, its unusual inclination, all these might be influenced by dark matter. Maybe BB isn't responding to a hidden planet. Maybe it's responding to a dark matter structure that passed through the Oort cloud 10 million years ago, set it on this trajectory, and then moved on, leaving no trace except the object itself. Future research will test this, combining cosmology and solar system dynamics, modelling how dark matter clumps evolve over time, where they go, how often they interact with the Oort cloud. It's interdisciplinary, ambitious, and it might rewrite how we think about comet injection rates. But here's the existential question. If dark matter shapes our solar system, if invisible structures dictate which comets fall inward and which don't, what does that say about our place in the universe? It says we're more connected than we thought, that cosmic scale structures influence local events, that the Milky Way's dark matter halo isn't just background, it's active, dynamic, shaping our neighbourhood in ways we're only beginning to understand. And if that's true, then studying BB isn't just solar system science, it's cosmology. It's a window into how dark matter works, how it clumps, how it interacts, and that makes BB even more valuable, even more mysterious, even more important. From the invisible pull of dark matter, we turn now to another cosmic mystery, one closer to home but equally strange, the tilt of our solar system. Part 12. The solar system's tilt mystery reopened. Our solar system is crooked. The sun spins. It has an equator, and that equator is tilted about 6 degrees relative to the plane where the planets orbit. That might not sound like much, 6 degrees, but it's weird, really weird, because the solar system formed from a rotating disk of gas and dust. Everything should be aligned, the sun's equator and the planetary orbits should match, but they don't. This has puzzled astronomers for decades. How did the sun get tilted? Was it always like this? Or did something knock it off axis? And if something knocked it off axis, what was it? In 2025, new research combining data from NASA's Juno mission to Jupiter and the European Space Agency's Gaia star catalogue reopened this mystery. Juno measured Jupiter's gravitational field with incredible precision. Gaia mapped stellar motions across the galaxy, and together, these datasets allowed researchers to reconstruct the early, dynamical history of the solar system with new accuracy. What they found was surprising. The tilt probably didn't come from the solar system's formation. It came later, from an external encounter, maybe a passing star, maybe a rogue planet. Something massive came close, exerted a gravitational torque and tilted the young sun relative to the planetary disk. This matters because if that happened, if the solar system experienced a close encounter early in its history, that encounter would also have affected the Oortcloud. Massively. It would have scattered objects, perturbed orbits, created the high inclination population we see today, and maybe, just maybe, it set BB on its current path. Think about it. If a massive object passed through the outer solar system 4 billion years ago, it could have simultaneously tilted the sun and destabilized BB's orbit. 2 effects. One cause, and BB has been falling inward ever since, slowly, over billions of years, until now. Let me explain what we mean by gravitational torque. When a massive object passes near a rotating body, it doesn't just pull uniformly, it pulls harder on the near side than the far side. That differential force creates a twist, a torque, and if the torque is strong enough, it can change the rotation axis, tilt it, reorient it. This happens all the time in the universe. Moons get tidally locked to their planets. Binary stars affect each other's spins. It's basic celestial mechanics, but applying it to the sun is tricky. The sun is massive, really massive. It takes an enormous force to change its rotation axis, so whatever passed by must have been huge and close, really close. Probably within a few hundred astronomical units, maybe even closer. That's uncomfortably close for a young planetary system still forming. The Juno data is crucial here. Juno spent years orbiting Jupiter, mapping its gravitational field in exquisite detail, and buried in that data are clues about Jupiter's formation and early evolution, how it migrated, how it interacted with other planets, how the entire solar system's architecture came to be. And when you combine that with Gaia's stellar motion data, which shows how nearby stars have moved over millions of years, you can work backwards, reconstruct ancient encounters, figure out who might have visited. The leading candidate is a star. Not our sun's binary companion, we don't think the sun ever had one that close, but a star from the same stellar nursery. When the sun formed, it wasn't alone. It was part of a cluster. Hundreds, maybe thousands of young stars, all born from the same molecular cloud. And in those early days, stars were packed close, much closer than they are now. Encounters were common, almost inevitable. So picture this. 4 billion years ago, give or take, A young star passes within a few hundred AU of the Sun, close enough that its gravity reaches inward, pulls on the outer planets, tugs on the Sun's outer layers, creates enormous tidal stresses, and over the course of the encounter, which might have lasted thousands of years, the Sun's rotation axis shifts. 6 degrees, not catastrophic, not enough to disrupt the planets, but enough to notice, enough to matter. Alternative ideas exist. Some researchers propose internal angular momentum evolution, the idea that the Sun's rotation slowed over time due to magnetic braking, and that somehow created the tilt. The Sun has a magnetic field. That field interacts with the solar wind, the stream of particles flowing outward from the Sun, and that interaction acts like a brake, slowing the Sun's rotation over millions of years. But here's the problem. Magnetic braking slows rotation. It doesn't tilt it. You'd need some asymmetry, some uneven distribution of mass or magnetic field, and there's no evidence for that. The Sun appears remarkably symmetric. So while magnetic braking is real, it probably doesn't explain the tilt. Others suggest asymmetries in the protoplanetary disk, gas flowing in uneven patterns, creating torques, nudging the Sun. This could work in principle. If the disk had large-scale turbulence, or if gas was falling in from a preferred direction, it could create enough torque to tilt the Sun. But again, there's no direct evidence, and the disk would have to be unusually asymmetric, more asymmetric than simulations typically produce. But these explanations feel weak. They require fine-tuning, special conditions. The passing encounter hypothesis is simpler, more robust. One big event explains multiple mysteries. A planetary scientist ran Monte Carlo simulations, thousands of them, modelling different encounter scenarios, different masses, different velocities, different trajectories, and only a narrow set of encounters produced both the solar system's tilt and the orbital distribution of Oort objects, including BB's perpendicular orbit. That's not proof, it's correlation, but it's suggestive, and it hints at something profound. Our solar system didn't evolve in isolation. It had visitors, interactions, close calls, and those events shaped everything. The Sun's tilt, the Oortcloud structure, the comets we see today. The simulations are fascinating. You set up a young solar system, planets still migrating, Oortcloud still forming, and then you throw in a passing star, vary its mass, its velocity, its trajectory, and watch what happens. Most encounters do nothing interesting. The star passes too far. Its influence is negligible, but occasionally you get the right combination. The star passes at just the right distance, just the right speed, and suddenly everything changes. The Sun tilts, the outer planet's orbits shift slightly, and the Oortcloud goes crazy. Objects get scattered. Some fall inward, some get ejected entirely, and the ones that remain end up on weird orbits, high inclinations, extreme eccentricities, perpendicular paths, just like BB. And if one encounter happened 4 billion years, go. Could others have happened more recently? Could there be a pattern of encounters, a rhythm, a cosmic drumbeat of passing objects that periodically disturb the outer solar system? Some dynamicists think so. They propose that stellar encounters happen roughly every 100 million years. Not exact, not predictable, but common enough to matter, and each encounter sends a new wave of comets inward, creating pulses of activity, clusters of unusual objects. The evidence for this comes from comet statistics. When you look at the arrival rate of long-period comets, objects from the Oortcloud, it's not constant, it varies. And some researchers claim to see periodicities, cycles, peaks and valleys in the arrival rate separated by tens of millions of years. Others are skeptical. They argue the signal is too noisy, too uncertain, but the idea persists. If that's true, then BB is part of a pulse, a wave, and there are others, already on their way, we just haven't seen them yet. And that's both exciting and terrifying, because it means the outer solar system is more dynamic than we thought, more active, more dangerous. But here's the really unsettling part. If stellar encounters shaped the Oortcloud, if they're responsible for sending comets inward, then predicting future arrivals becomes nearly impossible. Because we can't predict stellar encounters. Stars move chaotically. Gravitational interactions with the galaxy are complex. There's no simple formula. No way to say the next encounter will happen in X million years. It's random, stochastic, unpredictable. That means we can't forecast future BB-like objects with certainty. We can estimate probabilities. We can say statistically we expect one giant comet every million years. But we can't say when. We can't say from which direction. We can only watch and hope we have enough warning. But understanding the tilt isn't just about comets. It's about origins, about how planetary systems form and evolve, about whether our solar system is typical or unusual. And right now, we don't know. We need more data, more simulations, more observations of other star systems to compare. The good news is we're starting to get that data. Telescopes like ALMA and the James Webb Space Telescope are imaging protoplanetary disks around young stars, watching planets form in real time. And what they're seeing is surprising. Many of these disks are tilted, warped, asymmetric, just like we think our early solar system might have been. So maybe we're not unusual. Maybe stellar encounters and tilted disks are common. Maybe every planetary system goes through this. Or maybe we're special. Maybe most systems evolve in isolation, and we got unlucky. Or lucky, depending on your perspective. Because that ancient encounter, the one that tilted the sun and scattered the Oort might have been essential for life on Earth. Maybe it cleared out dangerous debris. Maybe it prevented a later catastrophic impact. Maybe we owe our existence to that cosmic near-miss. We don't know. We may never know for certain. But the pieces are coming together. The Juno data, the Gaia catalogue, the simulations, the observations of other star systems, all of it points toward a solar system shaped by encounters, by external forces, by a history more violent and chaotic than we once believed. And BB is part of that history, a survivor, a relic from an encounter that happened billions of years ago, an object sent on a slow journey inward, carrying with it the memory of ancient violence. And now, finally, after all this time, it's arriving, coming home, or perhaps coming to tell us something we need to know about where we came from, about how fragile our existence is, about how the cosmos shapes everything, even down to the tilt of our own sun. And speaking of cosmic mysteries, there's another one. Larger, stranger, more fundamental, a hole in the universe itself. And recent observations suggest it's deeper than we thought. Part 13. The super void anomaly gets stranger. The universe, when viewed at the larger scales, is not uniform. It's a cosmic web, filaments of galaxies separated by vast voids, regions where almost nothing exists, empty space stretching for billions of light years. And one of these voids is particularly strange. It's called the cold spot. The cold spot appears in the cosmic microwave background, the CMB. That's the afterglow of the Big Bang. Light from the early universe stretched and cooled over 14 billion years. The CMB is remarkably uniform. Temperature variations are tiny, a few parts in 100,000. But there's one region that's colder than it should be. Significantly colder. And astronomers have been arguing about it for 20 years. In 2025, a team reanalyzed CMB data from the Planck satellite and new ground-based surveys. They used improved statistical methods, better noise filtering, and what they found was unsettling. The cold spot is deeper than previous models suggested, more extreme, more significant. Why does this matter? Because the cold spot might be linked to a supervoid, an enormous region of space with much lower density than average. And if you look through a supervoid, light from the CMB loses energy. It cools, creates a cold spot. That's the theory. But the numbers don't quite work. The supervoid needed to explain the cold spot would have to be enormous, unusually enormous, uncomfortably enormous. Let me break down what we're talking about. A supervoid isn't just empty space. Space is already mostly empty. A supervoid is a region where even galaxies are scarce, where the average density of matter is significantly lower than the cosmic mean. And these voids can be huge, hundreds of millions of light years across, maybe 1 billion light years. That's bigger than galaxy clusters, bigger than superclusters. Its structure at the absolute largest scales the universe allows. When CMB, photons, those ancient particles of light from the Big Bang, travel through a supervoid, something strange happens. They fall into the gravitational well of the void. As they fall, they gain energy, blue shift. But then, as they climb out the other side, they should lose that energy, red shift. Normally these effects cancel out, but if the universe is expanding, and it is, The void grows while the photon is passing through it. So the photon doesn't climb out of quite the same gravitational well it fell into. It loses slightly more energy than it gained, ends up slightly cooler. That's called the integrated Sachs-Wolf effect, and it's real. We've measured it. But here's the problem. The cold spot is too cold, too big. The supervoid needed to create it, using standard physics, would have to be implausibly large, implausibly empty, on the edge of statistical impossibility. Not actually impossible, just really, really unlikely. And that makes astronomers nervous. Some cosmologists now wonder if the cold spot is evidence of something more exotic. Maybe it's a window, a glimpse into alternate physics, or maybe it's a scar, a mark left by colliding universe bubbles in a multiverse. Or maybe it's just statistical noise, a fluke, 1 in a million chance, and we're reading too much into it. The multiverse idea is particularly provocative. Some theories of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang, suggest that our universe is just one bubble in an infinite foam of universes. Each bubble has its own laws of physics, its own constants, its own properties, and occasionally these bubbles collide. When they do, they leave marks, scars in the fabric of space-time, and maybe, just maybe, the cold spot is one of those scars. The math works, sort of. Models of colliding universe bubbles predict cold spots in the CMB, but they also predict other features, specific patterns in the temperature fluctuations, specific statistical signatures, and so far, those haven't been conclusively detected, so the multiverse explanation remains speculative, tantalizing, but unproven. Then there's the exotic physics angle. What if the cold spot reveals something about dark energy? Dark energy is the mysterious force driving the universe's accelerating expansion. We know it exists, we can measure its effects, but we don't know what it is. And some theorists propose that dark energy isn't uniform, that it varies from place to place, and maybe the supervoid is a region where dark energy is slightly different, where the expansion rate is slightly faster, and that creates the cold spot. Again, the math kind of works. But there's no independent evidence, no other observations that support variable dark energy, so it remains a possibility, not a leading theory, just one option among many. But here's the speculative leap. If the cold spot is real, if it represents an actual anomaly in the universe's structure, could it affect local dynamics? Could gravitational effects from such a large-scale structure influence the oortcloud? Could BB be responding, however indirectly, to the universe's largest voids and filaments? It sounds absurd. The cold spot is billions of light-years away. BB is here, in our solar system. How could they possibly be connected? But gravity doesn't care about distance. It's infinite range. Weak at large scales, yes, but cumulative. And maybe, just maybe, the universe's structure creates subtle tidal forces that percolate down to small scales, affecting galaxies, affecting stars, affecting oortclouds. Think about it this way. We know galactic tides affect the oortcloud. The combined gravitational pull of the Milky Way's disk and bulge creates tidal forces that perturb distant comets. Those forces are tiny, but they're real, and they accumulate over millions of years. So what about larger structures? What about the pull from nearby galaxy clusters, from cosmic filaments, from supervoids? The calculations are brutal. You're dealing with forces so weak they're almost negligible. Almost, but not quite. Some dynamicists have run simulations, modelled how external gravitational influences from large-scale structure might affect oortcloud dynamics. And the answer is, maybe. It's possible. The effects are small, but over billions of years, small effects can produce noticeable changes in orbital distributions. If the cold spot represents a supervoid, and if that supervoid is relatively nearby in cosmic terms, maybe a few billion light-years, then its gravitational influence could subtly shape the orbits of the most distant oortcloud objects. Not dramatically, not enough to send them plummeting inward on their own, but enough to nudge them, perturb them, make them slightly more susceptible to other influences. And maybe BB is one of those objects. Maybe its orbit was shaped, in part, by the gravitational pull of cosmic voids and filaments. Maybe the reason it's falling inward now is because billions of years ago, the universe's large-scale structure gave it a tiny push. And that push, combined with galactic tides and stellar encounters and everything else, eventually sent it on its current trajectory. This is highly speculative, wildly so. Most astronomers would dismiss it outright. The effects are too small, too diffuse, too uncertain. But a few are intrigued, because if it's true, if cosmic scale structure really does influence local dynamics, then we need to completely rethink how we model the Oort cloud, how we predict comet arrivals, how we understand the architecture of the outer solar system. A cosmologist, after reviewing the new cold spot data, joked with colleagues, if the cold spot is a window, what's on the other side? It was a joke, but it's also a real question. Because if our universe is part of a multiverse, if other universes exist, then maybe the cold spot is where they touch, where the membranes meet, and maybe that has consequences. Imagine standing at the boundary between two universes. What would that even mean? The laws of physics might be different. The constants might vary. Time itself might flow differently. And if our universe is touching another one, if they're in contact, even briefly in cosmic terms, then energy could flow, information could leak, gravitational effects could propagate, and maybe, just maybe, some of those effects reach us. Reach the Milky Way, reach the solar system, reach the Oort cloud. It's the ultimate cosmic connection. The idea that an object in our solar system, a comet falling toward the sun, might be influenced by forces originating in another universe entirely. It's almost too strange to contemplate. But that's the nature of modern cosmology. We've pushed our understanding so far, explored scales so vast, that the boundaries between science and science fiction blur. But speculation drives science. It pushes boundaries. It asks uncomfortable questions. And sometimes, rarely, speculation turns out to be right. And if there's even a tiny chance that cosmic scale structure influences comet dynamics, we need to explore it. Because understanding BB means understanding everything, from the smallest ice grain to the largest cosmic voids. The cold spot might turn out to be nothing, a statistical fluke, a quirk of measurement, a reminder that even the most careful observations can mislead. But it might also be something profound, a window into physics we don't yet understand, a connection between scales we thought were separate, a hint that the universe is even stranger than we dared imagine. And if BB is part of that strangeness, if its journey toward the sun is shaped by forces operating at the largest scales imaginable, then studying BB becomes more than just solar system science. It becomes cosmology. It becomes a test of how the universe works at every level, from the quantum to the cosmic, from the local to the universal. That's the power of anomalies, of objects that don't quite fit, of cold spots and giant comets and perpendicular orbits. They force us to question, to investigate, to connect dots we thought were unconnected. And sometimes, in that process, we discover that the universe is far more interconnected than we ever realized, that nothing exists in isolation, that everything, from the smallest particle to the largest void, is part of a single, incomprehensibly complex system, and that understanding is changing, because we have new tools, new methods, new ways of modelling the universe, and one of those new tools is artificial intelligence, and it's already revealing things we never expected. Part 14, the AI that models the universe better than humans expected. Simulations are the backbone of modern astrophysics. We can't experiment on galaxies, can't rerun the formation of the solar system, so we simulate, we build computer models, feed in physics, let the code evolve, and see what emerges. But simulations are expensive, computationally brutal. Modelling the entire Oort cloud, every object, every interaction, every perturbation, would take centuries on current supercomputers. Enter artificial intelligence. In 2025, a team unveiled a breakthrough. A neural network trained on hybrid cosmology and gravitational data. It can predict large-scale structure formation more accurately than traditional n-body simulations, and it does it 100 times faster. Maybe 1,000 times faster. This is revolutionary, because suddenly, simulations that were impossible are now feasible. We can model the Oort cloud in exquisite detail, track individual objects over billions of years, test perturbation scenarios, and see which ones match observations. The AI works by learning patterns. It doesn't solve equations step by step. It learns from data, from previous simulations, from observations, and it finds shortcuts, emergent patterns humans missed. It's not magic, it's just pattern recognition at scale, but it's incredibly powerful. Researchers have started feeding it solar system data, known comet orbits, planetary positions, and they're asking it to predict where the next giant comet will come from, what its orbit will be, when it'll arrive, and the results are stunning. The AI flags perturbation signatures human modelers didn't prioritize. It suggests hidden influences, forces we haven't fully accounted for. For example, the AI noticed a correlation between BB's orbital parameters and the distribution of distant TNOs, a correlation so subtle that statistical tests barely detect it. But the AI insists it's real, and when researchers dug deeper, they found it might be linked to a past gravitational interaction, something we'd missed. This is the power of AI. It sees patterns we can't. But there's a danger. AI models are only as good as their training data. If the data is biased, incomplete or wrong, the AI will learn those errors, amplify them, and produce garbage predictions dressed up as breakthroughs. So scientists are cautious. They test AI predictions against observations. They compare different models, they demand reproducibility, and they never trust AI blindly. It's a tool, a powerful tool, but still just a tool. There's a story. A computational astrophysicist spent 6 months training an AI on 50 years of comet observation data. Orbital mechanics, brightness curves, spectroscopy, everything available. And then they asked it a simple question. Where will the next BB-sized object come from? The AI thought for hours, processing, calculating, and then it spat out coordinates, a specific region of the Oort cloud, a specific time frame, 20 to 30 years from now. The astrophysicist was skeptical. They checked the math, ran independent simulations, and everything supported the AI's prediction. But here's the uncomfortable part. The AI also flagged secondary predictions, things it noticed but couldn't explain. Anomalies in the data, perturbations that didn't match known physics, and when pressed, when asked to justify these anomalies, the AI couldn't. It just said, the pattern is there. That's both exciting and terrifying, because it means the AI might be seeing real effects we don't understand yet. Or it might be hallucinating patterns from noise, finding faces in clouds, and we won't know which until the future arrives and we can check its predictions. But the potential is enormous. Imagine combining observational campaigns, Hubble, ALMA, ground-based surveys, with AI-driven predictive models. We could forecast comet arrivals decades in advance, identify dangerous objects before they get close, plan missions with confidence. It would transform how we study the outer solar system. And for BB specifically, AI could help us understand its evolution, how its jets will change as it approaches perihelion, whether it'll fragment, what its composition reveals about solar system formation. We could run thousands of scenarios, test every hypothesis, and converge on the truth faster than ever before. But there's a philosophical question lurking here. If an AI tells us something we don't understand, something that contradicts our models, should we believe it? Should we trust a black box? Or should we demand human understandable explanations for every prediction? Different scientists have different answers. Some embrace AI fully. They argue that human intuition is limited, biased, evolved for survival on Earth, not for understanding cosmic mechanics. AI doesn't have those limitations. It can see patterns we're blind to. So trust it. Others are cautious. They argue that science requires understanding, not just prediction. A model that predicts correctly but can't explain why is alchemy, not physics. We need transparency, interpretability, human comprehension. Both sides have merit, and the debate will shape the future of astronomy. But for now, AI is here. It's being used, and it's changing how we study objects like BB, whether we fully understand it or not. The implications extend beyond just prediction. The AI is also revealing something deeper about how we've been thinking about the Oort cloud. For decades, we've modelled it as a relatively static reservoir. Objects sit out there, waiting. Occasionally something perturbs them, and they fall inward. Simple, clean. But the AI suggests something more dynamic, something more chaotic. When researchers fed the AI data on known long-period comets, objects that came from the Oort cloud in the past, the AI started detecting patterns in their arrival times. Not random, not quite periodic, but structured, like waves. Pulses of activity separated by millions of years, as if something keeps disturbing the Oort cloud in cycles. This matches some theoretical work from the 1980s and 90s. ideas about galactic tides creating periodic comet showers. But those ideas fell out of favour. The data was too noisy. The evidence too weak. But now the AI, processing vastly more data with far more sophisticated algorithms, is resurrecting those ideas, suggesting they might have been right all along, and if comet arrivals come in pulses, if BB is part of a wave, then we need to rethink our entire approach to planetary defence. Because it's not just about tracking individual objects, it's about understanding the cycles, predicting when the next pulse will arrive, preparing for multiple large objects, not just one. The AI has also started making predictions about the oortcloud structure. Traditional models assume it's roughly spherical, a uniform shell surrounding the solar system, but the AI suggests asymmetries, regions where the density is higher, clumps, voids, structure that reflects the solar system's journey through the galaxy over billions of years. Some of these predicted structures align with known features, the scattered disk, the inner oortcloud. But others are new. The AI predicts a concentration of objects in a specific direction, toward the constellation Perseus. Why? Nobody knows. But if it's right, if we point our telescopes that direction and start finding more objects, then the AI just revealed something fundamental about solar system architecture. There's resistance, of course. Some astronomers argue we're putting too much faith in machine learning, that we're letting algorithms drive research instead of human insight, that we're becoming passive observers, waiting for AI to tell us what to think. And there's truth to that concern. Science shouldn't be outsourced to black boxes. Human creativity, intuition, skepticism, these are essential. They're what separates science from mere data processing. But others counter that AI isn't replacing human scientists, it's augmenting them, doing the tedious work of pattern recognition so humans can focus on interpretation, on asking why, on designing experiments, on building theories. The AI sees the patterns, humans give them meaning. Together, they're more powerful than either alone, and for objects like BB, that partnership is crucial, because BB is complicated, multifaceted. It's not just an orbital problem or a composition problem or a perturbation problem, it's all of those simultaneously, and the only way to solve problems that complex is to throw every tool we have at them, including AI. The future of oortcloud research, the future of comet science, increasingly depends on these AI models. They're becoming indispensable, and as they improve, as they ingest more data and refine their algorithms, they'll only get better, more accurate, more insightful, more unsettling in what they reveal. Because that's the pattern. Every new tool, every new method reveals that the universe is stranger than we thought. Telescopes showed us distant galaxies. Spectroscopy showed us what they're made of. Computer simulations showed us how they evolved. And now AI is showing us patterns we never suspected. Structures we never imagined. Possibilities we never considered. BB is part of that revelation. A single object. A single comet. But it's teaching us that the outer solar system is more complex, more dynamic, more mysterious than we ever realized. And the AI is helping us see that, helping us understand, even if we don't fully understand the AI itself. And speaking of things we don't fully understand, there's one more cosmic mystery. One that strikes at the very foundations of physics. A theory that emerged in 2025 and sent ripples through physics departments worldwide. A theory that suggests our most basic assumptions about how objects move might be wrong. Part 15. The New Physics Rumour Mill, 2025's most controversial paper. In 2025, a paper circulated, not through major journals at first, through preprint servers, email chains, quiet conversations at conferences, and it proposed something radical, something that most physicists dismissed immediately. But a few, a small but growing few, found it impossible to ignore. The paper suggested that inertia, the resistance of mass to acceleration, might not be constant, might vary depending on cosmic environment. Specifically, it proposed that inertia changes at galactic scales, out in the deep dark between stars, in the outer reaches of planetary systems, where gravitational fields are weak and matter is sparse. In those regions, the paper argued mass behaves differently, not dramatically, but measurably. The motivation behind this theory is frustration. Dark matter explains a lot. Galactic rotation curves, gravitational lensing, large-scale structure. But it doesn't explain everything. There are anomalies, small discrepancies, weird behaviours at the edges of galaxies. And some physicists wonder if maybe, just maybe, we're missing something more fundamental than invisible matter. What if inertia itself is wrong? What if Newton's laws, refined by Einstein, are still incomplete? What if there's another layer beneath general relativity that we haven't discovered yet? The paper proposes a modification, a subtle one. At normal scales, near planets and stars, the modification is negligible. Physics works as expected. But at extreme distances, in the Oortcloud for example, inertia increases slightly. Mass resists acceleration more than Newton predicts, and over millions of years this changes trajectories, changes orbits, creates deviations. If this theory is correct, even partially, it could explain BB's orbit without invoking hidden planets or dark matter clumps. Because if inertia is different in the Oortcloud, then objects there evolve differently. Their paths deviate subtly from Newtonian predictions, and over billions of years those deviations add up, create high inclination orbits, create anomalies, create objects like BB. The criticism was immediate. The math is elegant, many physicists said, but where's the empirical evidence? How do you test this? How do you measure inertia at those scales? And even if you could, wouldn't we have noticed discrepancies by now? Wouldn't spacecraft trajectories show anomalies? The author, a young theoretical physicist, argued that we have noticed. Anomalies exist. Pioneer anomaly. Anomalous accelerations in deep space probes. Unexplained trajectory deviations. Most have been explained away. Thermal effects. Outgassing. Modelling errors. But maybe some are real. Maybe they're hints of variable inertia. The paper was submitted to major journals. Rejected. Resubmitted. Rejected again. One reviewer wrote, "This is mathematically interesting but physically speculative. Come back with data." Another wrote, "If you're right, you've just overturned 3 centuries of physics. Extraordinary claims require extraordinary evidence, but the paper found supporters. A small group of physicists who've been wrestling with galactic dynamics for decades, who've tried to make dark matter work and found it lacking, who are willing to consider alternatives, even radical ones. They don't fully endorse the theory, but they're intrigued. They're running simulations, testing predictions, looking for observational signatures, and here's where it ties to BB. If variable inertia is real, then every comet trajectory calculation we've ever done is slightly wrong. Not hugely wrong, not obviously wrong, but wrong enough to matter over billions of years. And objects like BB, which have spent eons in the Oortcloud where inertia is allegedly different, would show the effects most clearly. So studying BB becomes a test, a way to check if inertia really varies. If BB's orbit deviates from predictions in specific ways consistent with variable inertia, that's evidence. Not proof, but evidence. And if enough objects show similar deviations, the theory gains credibility. There's a story. The physicist who wrote the paper received hate mail, anonymous emails calling them a crank, a fraud, a disgrace to science. But they also received messages of support from researchers who'd privately wondered the same things, who'd seen the same anomalies and been too cautious to speak up. And one message said simply, "Keep going. You might be wrong, but you might be right. And if you're right, everything changes. That's the nature of revolutionary science. It's uncomfortable, divisive. Most revolutionary ideas are wrong, spectacularly wrong, but some aren't. Some turn out to be glimpses of deeper truth, and we never know which is which until we test them, until we gather data, until we let reality decide." So what does this mean for BB? It means BB isn't just a comet, it's a test case, a messenger. Whether it's revealing dark matter structures or variable inertia or hidden planets, or just standard comet physics scaled up, BB is teaching us something about the outer solar system, about cosmic forces, about the limits of our knowledge. And maybe that's the real story. Not that BB is unusual, but that it's forcing us to question everything, to re-examine assumptions, to consider possibilities we'd dismissed, to admit that despite centuries of astronomy, despite powerful telescopes and sophisticated models, we still don't understand the universe, not fully, not even close. BB is heading toward the sun, slowly, majestically, inevitably. And as it approaches, it carries with it mysteries, ancient ones, frozen in ice for billions of years, waiting to be revealed, and we're watching, studying, speculating, hoping to understand before it's too late. before it swings past perihelion and heads back into the darkness. But here's the uncomfortable truth. Even if we study BB perfectly, even if we map every jet, analyse every molecule, model every perturbation, even if we understand it completely, there will be others. More giants lurking in the oortcloud, more anomalies drifting inward, more mysteries waiting to challenge everything we think we know, because the universe isn't done surprising us. It never is. Every answer raises new questions. Every discovery reveals new ignorance. And objects like BB, objects that don't quite fit, that break our models, that force us to think differently, those are the most valuable of all. Because they're the ones that teach us we were wrong. And being wrong, admitting it, fixing it, that's how science progresses. So as BB continues its long fall toward the sun, as we watch and wait and wonder, remember this. This giant comet isn't just a relic, it's a messenger. Of forces we barely understand, of physics we're still discovering, of a universe far stranger and more complex than we ever imagined. And if we listen, if we pay attention, if we're brave enough to question our assumptions and follow the evidence wherever it leads, then maybe, just maybe, BB will teach us something profound about where we came from, about what's out there, about how little we really know. And that thought, that humbling, exhilarating, terrifying thought, should keep us all looking up, searching the darkness, waiting for the next giant to emerge, because they're out there, somewhere, drifting in the cold, waiting for their turn, waiting to challenge us, to surprise us, to remind us that the universe is vast and strange and full of wonders we haven't even begun to understand. The cosmic drumbeat continues, and we're only just learning to hear it.